Okay, let's take a look at how to design some of the IIR filters. And then basically first one is the one which is the only one that you can design by heart. So that's the band stop notch filter. Notch filter. Let me start from some parameters here. For example, sampling rate at 1 kilohertz. Oops. Nice try. Just an arbitrary number, right? Yeah, and then of course we have the line humming there, 100 hertz, right? That's the usual case. You have a measuring system and you see the peak when you do the analysis. Oh, there's something periodic, and then you do the quick spectral analysis and see, oh no, there's a 100 hertz peak there because of the electronic equipment, and especially if there are full wave rectifier that gives you 100 hertz. Right. Right. Not 50 hertz, but 100 hertz. Remember why? Full wave rectifier. Not like this, but you know, 2 bumps for each, full period. Oh, right. And that means that our notch frequency would be 100 hertz. So this component must go. Okay. And how do we actually do it? We do the create the filter bandstop notch filter, meaning that we have the omega of that notch is simply Fn divided by Fs times 2 times pi. So it's just linear dependence, just scaling or calculating the corresponding the normalized frequency as an angle. 2 pi means the same as sampling rate, and then basically you just have it the 2 pi times the ratio of that notch frequency divided by sampling rate. Easy. Okay. So that's the angular frequency, normalized angular frequency. Good. And now we know where to put the 0. 0 would be on unit circle at angle omega, but then in addition to the 1 0, we also need the complex conjugate. So that's one fast way of producing the complex conjugate pair. Oh, omega n. Yeah, did you mean? Yes, I did mean that. Okay, and now we could actually just use the z-plane to so that one single, well, the zeros, they are there. Makes sense. That's about 1/5 of the from angle from 0 to pi. Good. That's fine. Now we need the if we calculate, use this as the only to suppress that frequency, then basically we could already make the filter coefficients by saying polynomial which is defined by the 0. Same thing as I did on Tuesday. So this is the filter coefs. Okay, there we go. And this is now a FIR system. We have just the y equals to x plus or minus 1.618 times xn minus 1 and so on. But anyways, This is the frequency response of the filter, and as you can see, it's not really good for, it's filtering a little bit too much. It's filtering also the DC components is lower. Then it also has some gain at higher frequencies. So above 200 hertz, it starts to be a amplifier. So we need to do something about that one, and theoretically it should be just that we add that pole on the same angle. Okay, let's add some poles, but not just at any angle, but say we have the, we want that 3 dB half width to be, for example, 10 hertz. Why half width? Well, on that basically on this filter, when we are on this point, on minus 3 dB point here, that'll be this point, and then on the other side we also have minus 3 dB point if we are at the same distance there. Okay, so this is A, and then that one is also A. Together they are 2 times A. And we just need to change that 10 hertz again to the angular frequency. Omega dF equals dF divided by Fs times 2 times pi. This is the angular frequency again for this the 3 dB point, which is the same as the distance of the pole to the unit circle. So our range will be, actually we can do it like this: 1 minus omega dF times z. That gives the corresponding poles. So they are on the same angle, only the radius is different. Zeros are on the unit circle, meaning that you just use that the scaling factor and you got the poles. And we can then calculate the polynomial coefficients of the system just like that. Oops, no, not like that. PP, yeah, poly PP. There we go. So now we have both A and B's, so we can actually calculate what is the corresponding frequency response. And yes, I got everything quite okay. There we go. So minus 3 dB half width is 10 hertz. Good, it worked. Good. Good for you. Good for me. Next part actually on the this exercise is to again, okay, you know how to also do the impulse responses, so that's the third part. Design an IIR low-pass filter with the following properties. Wow. Compared to previous filter with the exercise 4.3. Wow. Okay. So this is more design. So let's continue with the filter designer. Filter designer. There we go. And take a look at the IIR systems. What kind of IIR filters actually we have? Practically, I would say only that makes really some sense on the classical ones is the elliptic the filter. and just to give it some hint of how this one works, you define the cut-off frequency and stop and start frequency, and then what is the passband ripple and the stop band, the attenuation, and in click design filter, and gives you something like that. So actually elliptic filter is quite nice for the IIR filter, since there you have control on how much you actually tolerate stop the passband ripple, meaning variation of the amplitude response, and then it also gives you quite constant the stop and attenuation level. So it's quite optimal, quite optimal. Okay, so yeah. You could actually go a little bit lower order, I think, since it's this stop band actually starts a little bit earlier. Haha. Okay, well, this is not science. Yeah, this is how you create the filters, and it does not change much from this FIR system, except let's see, if we compare the same design. So this is the FIR. We get filter order 25. But in IIR, same parameters for the filter, we get 6th order. Okay, 6th order FIIR means it means 3 second order sections. Each second order section, or actually one section takes it's order number. Wait a minute. Each order number for IIR means the double the order number of multiplications, and additions takes about 12 multiplications. The other one takes 25 multiplications. So the cost factor is actually 2. FIR, although it's stable and everything, but anyways, IIR, it's much more cost efficient to implement. Less operations, meaning you can do more with your processor. Okay, so basically these designs here, classical design for Butterworth looks like that, because all of the zeros are packed in one place. But it still has the amplitude response is flat on the passband. Then let's take a look at the Chebyshev type 1. Okay, so it actually we can tolerate some the ripple on the passband. So it is constant ripple on passband. The Chebyshev type 2, practically we have the control on the stop band attenuation. It's constant and basically a flat passband. Okay, how that one is done. Okay, these the poles are actually such that it flattens the passband, and zeros are such that you get equal amount of the stop and attenuation over the spectrum. Okay, and then this elliptic was the one which combines basically Chebyshev 1 and 2. Maximally flat. Okay, there you can actually, it makes it maximally flat that you can actually fix the filter order in both numerator and denominator separately. So this is kind of funny kind of filter type. Here we have the least norm. Okay, yeah, that's another way of uh, creating a filter. It has some benefits over the others. And so on. But say on the audio information, I would go with the elliptic just because there's enough of control on the parameters. For the when the linear phase response is required, then the only way to go is the FIR. Okay, so yeah, so basically you just click the buttons and you get whatever is required on the exercise. And then, you know, copy this screen, make a screen dump and put it there when you get it done, when you think it's okay. Okay, one more thing actually, I'll show you, because you're supposed to be able to also implement these filters. And now we have sixth order filter so that it actually has 3 sections, meaning it has been broken down into 3 cascaded second order systems for the reasons we talk about tomorrow. But anyways, this is how you implement second or implement this IIR system. And then you have this, each section has numerator coefficient and numerator coefficients and denominator coefficients and gain, for the reasons we talk more about tomorrow. But anyways, this is more or less compatible with the, if you basically just generate the header, coefs IIR. This is quite the same, quite compatible with this. Where did I have it? I had it somewhere out the ARM DSP library. Keel, yeah. There we go. Come on. It takes a while. It's there. So practically that library has same components as what we get out from this one. So basically this the IIR filters are broken into these cascaded second order sections, meaning that okay, maybe that will go and that goes to first section 1, output goes to section 2, and then we have output goes to section 3, and each of these sections are actually let's see, I think they are done this way. So they have common things there, and then we have even one section here. So okay, there. It goes something like this. Oops. So B0, B1, B2. A1, A2, and then we have the gain, common gain. Practically, why there's a common gain factor and then why these are broken into three different parts or actually second order systems is the computing accuracy. That way you can optimize the or minimize the calculation error. Okay, so yeah, there's again something that you can just include as a code to your own program. One more thing. How about if you want to continue checking this filter on MATLAB? You can actually export this filter as coefficients, okay? Either coefficients or objects, maybe objects. Yeah. To MATLAB workspace, and after that you can actually do, for example, things like Z-plane HD. So you can continue working on this one instead of BBAA pair. This is actually an object which has the second order system inside of it. What does this look like? I think if we can open it. Property inspector, initializing way. Wait. Okay. So basically it is an object. It's not just numbers. It also have some values. Oops. Let's not change anything. But anyways, then if you want to use that as a filter, then you have instead of that, for example, like this, and then 100. This is how you use it as a filter. Instead of BBAA, you just ask the HD instead. There you go. So that kind of filtered value came out. Good. So yeah, what else was there for today? Compare and design an IIR filter. Okay, the part 9 and 10. Oh, I need to change those values. I will make those minus 12 dB and this is minus 25 dB. Okay, now that changed. Okay, if you did already open this template, go and take these numbers for the last one. If you amplify a voice too much, it actually saturates. It sounds really bad. Now it's fixed. Okay, so basically the part 9 and 10. Oops. 9 and 10 of this exercise are quite fun. It's about how to make the tone control of audio. Human ear on body diagram. You can hear from 20 Hertz up to 20 kilohertz. I cannot. I'm older. Yeah, so I can hear maybe something like up to 15,000 Hertz or something like that. I doubt that no higher than that. 200 Hertz, 2K Hertz. So this is your hearing area, somewhat. actually, that marks pretty nicely the if you basically cut the or separate or divide the hearing area with low frequencies, middle frequencies, and high frequencies. But those are basically the high frequency. So bass, middle, distant, okay, D. Those are the areas. Because human ear actually is logarithmic, so we actually sense the frequencies so that, for example, if you double the frequency, it sounds like it just step up, 1 unit. When you double that, it sounds like it, again, the frequency change 1 unit. This is just human physiology. Okay, so you need to make some filter banks. One low pass filter for bass, band pass filter for the middle, and then high pass filter for the higher frequencies. Okay. I'm not using colors now. Okay, so middle would be that black, and red would be this one, and then we have the distant. And adjusting the tone level of some voice, meaning that you will be basically either going up or down within the volume. So the whole system to adjust this, adjust the tone would look like this. So you have 3 filters. One for bass, then middle, then distant, and with adjustable gain, and sum the out. There you go. The rest of that exercise you can now probably imagine. So yeah, 3 different filters. You run the signal separately through each of these filters, which are designed on the filter designer. Then you have basically 3 different gains. So bass is just gain of 1. Middle has minus 25 dB. Oops. Gain. And this one has minus 12 dB gain. There. And now a little bit of a trivia. Why you usually on the car stereo have only adjustment for bass and high frequencies? Because third one is the volume. You just need to adjust those 2 related to the middle one. Okay, good. Whoops. Let me take a quick look. Exercise 5. I think we changed the deadline for this exercise 5 until tomorrow, since it would be probably a little bit too much to ask 2 exercises done at one day. Maybe. Right? Sure. And your fellow students will thank you. I will make my the phone to wake me up at 1 a.m. No. Okay, tomorrow. That'll be deadline for the 5th exercise. Okay, good. Any questions? Yeah, I know. No, I know. Did anyone promise that this would be easy?